In theory,
it's exhaustive search.
It will run.
Yeah.
But the performance side is very bad. The bad thing is a performance compromise are two layers. One is that this is a full system virtualization. Or actually, I prefer to use the simulation. The difference is that when we are using QEMU for x64 to run the Windows VM or run a Mac OS VM, we usually compile with the KVM mechanism. So KVM will directly make the simulation, directly ship that blocks of code into the host CPU and directly run it without any interpretation of the instructions or simulation of the instructions. So by introducing KVM here, it's like the performance compromise is like just let's say 20% or 30%. That's great. However, if the host is like this, for other architectures you cannot enable KVM because you cannot directly run ARM instructions on a Intel CPU, so you cannot using KVM. So which means that, for example, if there is an ARM instruction here, it will be interpreted by the VM system and to translate it to a bunch of Intel instructions and to run it. So that will introduce the performance like maybe 10 times to 50 times differences. It's not percent, it's times. Yeah. So that's exactly why the Android, because Android is based on QEMU ARM. That's why Android virtual machine is pretty slow. That's the reason, because it's a simulation execution. It's not actual host virtualization. So first of all, you can see the whole Linux system itself being simulated execution. So only just the Linux system boot up, it may require like 5 minutes or even more, or even worse. So you can know this is a full system simulation. This may have a lot of problem. And secondly, to monitor the behaviors, there are two solutions, as you said. One is that hooking. However, what we choose to do is tracing. There are basically two different ways. One is the hooking, that means I modify the system code to add some stuff into the system code, so that you invoke this syscall, I will know it, right? Another way is tracing, which is rely on systems mechanism to say I have some monitor point there. If you go through that, I will know it, but it's not in real time. It's maybe like 10 milliseconds delay. And you already passed through, but I just get to know it. That's but anyway, by either way, you will know that it did something on the system layer. However, the problem is that hooking or tracing is usually between the system and the malware execution is here. So let's say here is the monitoring. Monitoring itself usually will also introduce like by experience, will also introduce like 5 times to about 20 times performance compromise. But this compromise is not to the full system, it's to the malicious program you are running, to that single process. So let's calculate it. By full system simulation, you introduce like 10 to 50 times, right? So multiply it, it means like it's maybe like hundreds to thousands of performance delay to this malware simulation. But that means, for example, if our system to set up a reasonable time, say, let this malware to run like 5 minutes, which is current time in wild file, that means it actually just run normally at 2 seconds. 2 seconds, you cannot trigger any behavior, because that's just the beginning, very beginning. Otherwise, you may run it like for 2 hours, maybe enough, but that's 2 resources occupation, you know. So this one is very hard to be reduced because
and just because we're arguing, so that this one being the 5x to 20x time
or maybe less, but it will definitely have like tens of differences of compromise. This one is very hard to be reduced because that no matter using hooking or tracing. But this time, multiple like this will tell you why this naive solution don't work.
Yeah, times 7 for each of the architecture.
I believe this is main reason why those open source solution didn't do it. Didn't implement it because this doesn't work. This is also why in the beginning of last year we thought we won't have a dynamic analyzer for Linux IoT because of this calculation. Okay. However, let me see. The third problem we are resolving is the maintenance. So if we're doing a system like this, for maintenance, that means that we will need to maintain like about 7 to 10 different virtual machines with different hooking, monitoring or hooking tracing per architecture because the syscore is different per architecture. So any kind of bugs, you need to upgrade all the virtual machine images, you need to upgrade all the guest code and push it to production, like thousands of actual servers, right? So that will be a huge complexity of the maintenance. That's something in the file size. We never do that. For example, in the Windows, we just have two different, which one is for Windows 7 and for Windows 10, two images, that's all. So every time we need to add something new, to create something new, we just create two new images. But this one it will be like introduce 10 more, which introduce the maintenance problem. So,
let me take a picture real quick.
Okay. Let's take a look at the new solution.
Did I got everything right in my program?
So it's right because the reflections.
Yeah.
Yeah, I think. Yeah, I have it. Okay.
Okay, thanks.
So the challenge is already clear, right?
Yeah.
Okay, cool.
Just want to make sure I caught it before you read.
Yeah.
So the new method, the idea is kind of simple, but implementation is hard. So I will introduce the idea first. Okay. The idea is like the host is in the host layer we still using most common like x86-64 hardware. So this is still a traditional solution. This is still the most popular server you are using. We did actually consider about using ARM server, but it can be extended to MIPS or other architecture. Anyway, so for the host OS, we still using like Linux 86-64.
And I assume it doesn't really matter if it's Ubuntu or Debian or whatever.
It's not matter. It's not matter. Yeah.
Okay.
Well, for the
Red Hat
VMM, we're using simple QEMU x86-64 with KVM feature. Okay, so which means that there's no performance differences. Well, the guest OS, we're using any kind of right now we're using Debian, but any kind of Linux 86-64 are good. Then the problem is how to run it.
Right.
So QEMU has actually this program has two different kinds of things. One is called a QEMU system. The actual thing used here is
QEMU system?
QEMU system.
Okay.
Which is used for whole system simulation. Well, it actually has another set of QEMU, which is QEMU. Sorry, it's MU.
Yeah, that's fine.
MU. QEMU is usually people call it a QEMU user space. Which is used to run a single user space program as a single process. So, for example, if you compiled a hello world into the ARM architecture, cross-compiling to ARM architecture, well, that hello world, if you statically linked it, which means it's self-contained, well, on an x86 machine, you can run that piece of code via QEMU user space. So how it works is that QEMU will read that binary, load it into memory and to read the instruction which is ARM and translate it into Intel and execute it, ask the host to execute it. So that's the basis of how this works. But it's just applied to